Good morning, everyone. My name is Anant Vijay, and I'm from ISAR Kolkata. And today I'll be talking about how we can simulate or realize non-Hermitian PT-symmetric dynamics of a many-body system, in particular, a multi-spin quantum system. And this work has been done under the supervision. I hope the pointer is
Yes, Anant is
yeah,
visible.
yeah, sure.
Yes.
Okay, thank you. So this work has been done under the supervision of Dr. Sorindas from ISAR Kolkata, and here is the reference where you can look for the elaborate details of this work. So uh, a generic non-Hermitian two-level system can be represented by can be written down in such a form where imposing the conditions that A is perpendicular to B and mod of A is greater than mod of B would ensure that such a Hamiltonian has real eigenvalues. Now, the dynamics of a given state under such evolution, which is governed by this non-Hermitian Hamiltonian, can be written down with this dynamical equation here, which has three different terms. Now, after these three different terms, two of the terms are linear, and the other final term that you can see here is a nonlinear term. Now, important to notice that this nonlinear term is what distinguishes this non-Hermitian dynamics from the other non-unitary dynamics like Lindbladian dynamics, Markovian dynamics, where the dynamical map is a linear map. And the solution to this equation here, as we can see, can be written down in this form. And where the thing to note is that the solution is such that if we plug in a pure state here, it remains pure, so such that the dynamics always remains on the Bloch sphere. Now, the details of how an arbitrary mixed state evolves under such dynamics can be found in this reference here. And the point is that this dynamics is strange in a sense that this dynamics does not obey the laws of quantum
Sorry,
mechanics. Yeah. Hello.
sorry, can you hide this Zoom window because I couldn't see the reference and it's still
Oh,
there.
sorry. Yeah, fine.
Thanks.
Okay, so here, this is the reference. Um, okay, so now this dynamics does not really obey the laws of what is allowed by the quantum mechanics, as we found here, that for a two-level system which is governed by such a non-Hermitian Hamiltonian, would would give would provide an extreme speed of evolution to the quantum state which has been shown here. In other words, the state of the evolution gets accelerated extremely, such that the temporal correlation which have been represented here in terms of what is known as Leggett-Garg inequality can go beyond what the values are allowed for correlation in the quantum mechanics. And in fact, this correlation can go up to their algebraic maxima, and this maximum can be then found to be connected to what is defined the non-hermiticity of the Hamiltonian with a single parameter theta as so the extreme speed leads to extreme violation of these correlations, and the details of which can be found here. And so the point is that now this dynamics does not really follow the quantum rules, so it is natural to ask that how we can really realize such a dynamics by within the frame of quantum mechanics. So as it turns out, there have been proposals where this where the where there where there has been discussed that how we can realize such a non-Hermitian dynamics using Hermitian Hamiltonians, where in this first proposal what has been said is that using a Neymark's dilation theorem, what we can show is that a non-Hermitian system can be interpreted as a subsystem of a larger Hilbert space, which can then be defined as a Hermitian system. And similarly, followed up by this proposal, another proposal where there have been realization of a two-level non-Hermitian dynamics using what is known as the embedding or the dilation method, And the point is here, in this particular reference, only the PT-symmetric dynamics have been realized. And then later on, these people found that even the PT-symmetric, PT-broken dynamics can also be realized by expanding the dimension of the Hilbert space and doing the projective measurements on it. So let me just go quickly through what can be done here. Now, the idea is to bring in some extra degrees of freedom, and which we are going to call ancillary degrees of freedom, and then we are going to define or custom design total Hamiltonian and the initial preparation of the state such that the subspace dynamics here follows a is a non-Hermitian dynamics as we desire upon projection of this ancillary degree of freedom on a particular state. In this case here up, if you projected the ancillary degree of freedom on up, we'll end up with a state psi which has been evolved by a non-Hermitian Hamiltonian H theta. And now what was pointed out as well in this paper, that this kind of formalism not just restricted to only a two-level system, but can be extended to any arbitrary n-dimensional system. So following this this line of thought, what we have done here, we have considered simulating non-Hermitian dynamics of n-free non-Hermitian spin halves, and by using a minimal coupling with bringing in some 2 extra degrees of freedom, which we are going to call ancillar spin. And as a result, as it turns out, that even this simplest dynamics, non-Hermitian dynamics of n spins, would result in a very complicated complicated Hermitian Hamiltonian, which comprise of now n+1 spin-half particles, and which has Q-body all-to-all interaction terms in it. So let me just go through now what is the recipe, what is the generic recipe to how we can obtain such a non-Hermitian dynamics by expanding the Hilbert space for any arbitrary Hamiltonian. This follows, and the only thing that we need to know, that we start with an exactly solvable many-body Hermitian Hamiltonian, which we are going to call seed Hamiltonian. And then what we're going to do, we're going to apply this similarity transformation over it, which, for example, could be like this, can be a local similarity transformation or can be a non-local similarity transformation. And then this would lead to a PT-symmetric counterpart, which would give us the same resulting eigenspectrum as it has it for the seed Hamiltonian. And then what we do, we bring in another spin, and then we write down such a custom design total Hamiltonian, such that we get the Hermitian Hamiltonian in a larger Hilbert space, which would then have all these kind of interacting order terms. Now this H1 and H2 can completely be defined by using the operators H and P here, where H is the Hermitian Hamiltonian and P is the similarity transformation. All right. So now we start with a Hermitian Hamiltonian, which is a set of free Hermitian spin half particles, and then we do this kind of similarity transformation, which is local in nature. Now I'll tell you why this locality is different from the non-local similarity transformation. Now that would give us the equivalent counterpart, which is now the HPT symmetric, and still we can see that this PT symmetric Hamiltonian is comprising of n free spin half PT symmetric particles yet. And the reason to apply this local similarity transformation is that we want to keep the identity of individual spins intact, meaning that the property, the commutation property of these individual Pauli matrix, Pauli spin operators remains the same. So what we can do, even we have written down this PT symmetric Hamiltonian, we can interpret individual spin to the corresponding Hermitian Hamiltonian spin here. Now that we have set with all the ingredients, we go ahead and write down these operators H1 and H2, which depends in turn on these P and H, and then we again write down the total Hamiltonian in the larger Hilbert space, and then we can do the same thing with the initial state as well. We can define this certain state in the larger Hilbert space, which corresponds to the n+1 spin, spin-half particles. This would again lead us to the dynamics in the subspace of the PT-symmetric Hilbert space, where upon projection on this extra ancillar degree of freedom would lead us to this non-Hermitian PT-symmetric dynamics that we desire to simulate. But as it turns out, when we go ahead and write down this total Hamiltonian, which is the custom design Hamiltonian, in terms of these local spin operators, what we end up with is such a complicated many-body interacting Hamiltonian, where one can see that even though we started with a free Hamiltonian, we ended up with the Hamiltonian which has all ordered terms in it, two body, three body, up to starting from one body term to n plus one body terms. Now we try to focus on these coefficients and look at their amplitudes, that how they're behaving. So in order to do that, we take a particular case of only two spins, where we have two Hermitian spins to start with, and then we give them the similarity transformation, which would lead us to two non-Hermitian PT-symmetric free spins, and which then we embed using another single spin, which would lead us to this following Hamiltonian here, where this can be noted that these particular coefficients that we were interested in has amplitude like this. So important to notice here that the first single body term, the amplitude was the largest, and then they kept on decreasing. And on the contrary, we can see these other coefficients B1, B2, and A2 are non-zero and become equivalent to the single body term itself in the extreme limit of this parameter alpha. Now this alpha has been defined, this gamma has been defined in terms of parameterized in terms of this alpha here. So basically all these coefficients here depends only on two parameters. One is gamma, and another is this n. So these are the two parameters on which all these coefficients here that we see depends. Now, recalling that if we evolve such a custom designed state with this complicated total Hamiltonian, we'll end up with such a dynamics where the PT-symmetric part of the Hilbert space would get evolved through this HPT. Now, important to notice that if this psi PT, if we choose to be the eigenstate of this HPT, what we can do in this particular scheme is that we can write down this eigenstate, because now if psi PT is an eigenstate of HPT, this we can take it out as a phase vector, and we can define the eigenstate of such a complicated Hamiltonian here, this H total, the states we can define like this. So there, as it turns out, that these states are doubly degenerate in nature, and not just that, since these are doubly degenerate, what we can always do is that we can rewrite them in terms of some separable set of states, where this ancilla, which is the extra degree of freedom that has been brought in, is separated always with the rest of the PT-symmetric spins that we brought in as to simulate. So now this psi PT is related to the eigenstate, is related to the state of the Hamiltonian, this seed Hamiltonian, by this similarity transformation, and the corresponding eigenvalues we are representing here with using epsilon k here. So so that is how we get a full set of eigenstate for such a complicated total Hamiltonian, and these states are exact solutions to that H total, and they are also separable in their ancillary and the rest of the PT degrees of freedom. So now we take a look at complementary point of view here. Now, instead of treating that ancillar degree of freedom as same as the rest of the system, we treat it as a different, because now what we do, we take this ancillar degree of freedom and treat it as a qubit, while rest of these guys, which are these PT symmetric free spins were there, we treat them as a path for this ancillary degree of freedom. So now if we do that, what we have shown here, that in the particular case of ground state, if we choose this state to be the ground state, where the psi 0 can be defined as also all spins down in the along the x direction. What we then show that applying because since these states were doubly degenerate, what we first do is that we first leave the degeneracy by applying a magnetic field by adding an extra term into this total Hamiltonian, which is represented here as my sigma y. So what we are doing, we are applying an extra magnetic field on this ancillar degree of freedom, which would then lift the degeneracy of these guys and would give them energy, will split them by energy like this. So, and then what we found that the probability that flipping this ancillar degree of freedom now by using any anisotropic magnetic field. So let's say if we now apply an extra magnetic field along the z direction to these spins, the probability of happening that is turn out to be proportional to what these b plus and b minus mod square. Now these b plus and b minus, to remind, is are the PT-symmetric part of the total state, where we have taken the state to be in the ground state only. So this, as it turns out, that we have a two state which are separated by this energetically separated by this this gap, and it turns out that the flipping probability of this ancillar spin is turned out to be directly proportional to only these two states, which are now the ground state and the first excited state. So
Anant,
yeah.
Sorry to interrupt. You have about 5 minutes.
I have 5 minutes. Oh, all right. Thank you. So now what we found that these two states can be in the full parameter space. What we found that these two states can be orthogonal to each other, and orthogonality in here would mean that this term on the right hand side would become 0. So the possibility of flipping of this ancillar spin on the application of such a magnetic field which is along any anisotropic axis to this ancillar spin would become 0. So in that sense, this extra ancillar spin gets a protection from any arbitrary magnetic field which is applied perpendicular to its direction. And we also found that in the full subspace of these parameters, which are again defined by only these two variables, gamma and n, these two states can also become parallel. And in fact, even for a very large number of spins, we can show that there exists a limit where this orthogonality can still exist. So this ancillar spin is now protected against any magnetic field, which is if we are in this region of parameters here. And this orthogonality, as it turns out, is not an ordinary orthogonality, because now as we increase the dimension of the Hilbert space, what we can show that any two random unit vectors, their average overlap amplitude can be written down as 1 over 2 to the power n, or these two states, which are b plus 0 and b minus 0, these could also have been two separable states. Even in that case, we can see that it's directly proportional to cosine beta to the power 2n. So the point is that the orthogonality of two many-body state could exist in a large Hilbert space just because of the dimensionality of the Hilbert space. Like the first case, this could be the case that we can still get for large, and we'll get the 0 here. And if this cos beta is any small value than 1, then we'll still for large, and we'll still get the orthogonality. So as it turns out, that the orthogonality that we have here is not either of these. Instead, what we can show that this orthogonality can be written in this form, which it can be checked that this first orthogonality and second this expression does not really match. And what we have shown here that that we will try to compare these two functions f2 and f3, and as it turns out that they are not comparable throughout the stretch of number of spins, which means that this orthogonality is not due to the fact that these two states, b plus and b minus, that we have here are two product states, and so then definitely these two states, b plus and b minus, definitely are some two entangled states. And this orthogonality is not just a consequence of the increase in the dimensionality of the Hilbert space. that I would like to conclude that the idea of embedding that we have shown for many body systems, and as it turns out that even as simplest systems would then lead to an emergent interaction for the local PT-symmetric degrees of freedom. And an example, we have shown that that this extra degree of freedom which has been brought in to simulate this whole dynamics can enjoy a protection against decoherence due to the coupling with the rest of the path spins, which are the non-Hermitian spins that we simulate in the beginning. Okay, so the rest of the details you can follow up on this paper. Thank you.
All right. Thank you, Anand, for this nice talk. So if anyone has question, please unmute yourself and ask.
Hello.
Hello.
Yeah, Archit, go ahead.
Hi. Hi, Anant. Thanks for the great talk. And so I was, so I probably you said this, but I did not, I'm not completely sure. So this mapping from PT-symmetric Hamiltonian to this, the thing with the ancillas, I mean, sorry?
Hello.
Yeah. So this mapping, is that unique or no? You can make very many different mappings.
Okay, yeah, fine. So pardon. Yeah, so actually you can do all. This is not unique at all. In fact, this bringing in only extra 2 degrees of freedom itself is not unique, and one could have brought in many spins as well there to write down such a scheme, and it's not restricted to. I mean, in both the sides, it's not restricted. You can bring in some extra degrees of freedom of any dimension you like, and that can. And in fact, this formalism itself is not unique. One could have chosen a different way, but here the motivation is to take a simplest example. So we have only considered a minimal extra degrees of freedom which are required to simulate such a dynamics.
Okay, thanks.
Any further question? Okay, looks like there is none. All right, Anand, thank you so. Oh, sorry. Is there a question? No. Okay.
No,
So,
yeah.
All right. So thank you very much, Anand, and we'll move to our final speaker for this session.